Hi everyone, and this should be the last lecture video for chapter 16. And there is a category of reactions that I didn't talk about, and that is nucleophilic aromatic substitution. Now, this is not as common as electrophilic aromatic substitution, but I'll go ahead and give you an example. Under extreme conditions, what do I mean by extreme conditions? I mean like 350 degrees Celsius and potentially pretty high pressure too. So we really heat the hell out of this stuff. What do we get? Well, we get a substitution reaction, but instead of having a hydrogen substituted for an electrophile, we have a halogen substituted for a nucleophile. So NaOH, that's OH minus, and that functions as a nucleophile. And it will substitute for the bromine. Another type of reaction we could do and let's go ahead and let's put a chlorine there, why not? We'll use two equivalents of ammonia, and again heat and pressure, like 100 atmospheres or something, maybe even more than that. And we will get the following nitroaniline. So some things to note here. The bromine slash Cl is our leaving group, and that gets substituted. Gets substituted for nucleophile. OH minus or NH3 in these two cases. The mechanism is one that I'm not going to hold you responsible for, although you can read about it if you want to. It's what is called addition elimination, or sometimes referred to as SNAR, for substitution nucleophilic aromatic. So it involves the nucleophile adding and then an elimination occurring. When the nucleophile adds, you actually end up getting a carbanion intermediate, and the carbanion is stabilized by the nitro group. So one or more nitro groups is necessary. And these have to be ortho, let me actually rephrase this, I'm going to say para slash ortho to halogen leaving group. Typically para is more common, so that way you don't have any steric hindrance, but you can put multiple nitro groups on here. So if you really do want some information about the mechanism, you can go ahead and take a look in the text, because there is a description. All right. Now, there's another type of nucleophilic aromatic substitution reaction that involves taking halobenzene, like for example chlorobenzene, and then again heating it up with NaOH, and typically a bunch of pressure, and then quenching with acid to make phenol. We can also make aniline using NaNH2 and liquid ammonia followed by H3O+. But again, we have to use very stringent conditions here. So I haven't mentioned, sorry, NH2, I haven't mentioned the, you need heat and pressure for both of these. And these reactions proceed via a different mechanism. They proceed via an elimination addition mechanism, otherwise known as a benzyne mechanism. And that involves the formation of benzyne. And this is highly unstable because we're trying to get an sp hybridized, so this triple bond here would be sp hybridized carbons. They want to have a bond angle of 180, but we're trying to get them into a hexagon with a bond angle of 120. So this is very unstable. Very unstable. And again, if you want to look at a mechanism for elimination addition, the benzyne mechanism, it is in the text. But again, I'm not going to hold you responsible for these mechanisms. That said, I think these reactions, the addition elimination reactions, can be useful in synthesis. For one thing, it's a way to make a substituted phenol. You actually can nitrate a phenol, that's not a problem. But making a substituted aniline like this may be tricky because your typical nitrating reagents are strong acids, and they would protonate the amine here and deactivate the molecule. So this could be a good way to make paranitroaniline. So yeah, these may have some synthetic uses. All right, well, that's the last lecture. Go ahead and practice those mechanisms and synthesis. And we will talk more about aromatic reactions and stuff when we meet in person. All right, until then, stay safe out there. Bye now.